Alrighty, welcome back to operating system. So today's light, yikes. All right, so first, so lab 3 is coming up. Hopefully you're almost done with, or lab 4 is coming up. Hopefully you're almost done with lab 3. Please provide some feedback because I don't even know if the video I posted about lab 5, old lab 5, new lab 3 was even useful. So if that was useful, you should probably let me know and then you get more of it. So I have no idea. No one's given me any feedback so far yet. Very useful. All right, so good. So I assumed it was useful, but again, please share stuff with me if you like or don't like anything. We will do essentially a lab 4 help video next lecture. So I will teach you how to use things because you are going to implement threads. So this is a prelude to that lab, and then we'll get into implementation stuff to help you along, and then you should be able to go do lab 4 really quickly. There's some encouragement in lab 4 to get you to start thinking about it early, so you get to submit your own test case and figure out, and you can see how things run. Your test case you submit will be run against the solution, so you will be able to see what the answer is supposed to be. So you get a week to do that. It's only worth 5% of the total grade, so not much. So if you want to skip it, go ahead, but I encourage you not to. Just write your own test case. Anything that is tricky at all, just write in a test case and you get to run it against the solution and see what the actual answer should be. So if we are implementing threads, there are a bunch of different models we can do. So if we implement threads, we essentially have two choices. We can either implement user threads or kernel threads. So user threads means they are completely implemented in user space. Your process just has one thread that the kernel knows about, and it doesn't treat it any differently. So if one thread blocks, then all the others block because the kernel only knows about one thing. If, on the other hand, you have kernel threads, they are implemented majorly in kernel space, and the kernel actually can schedule them. So it can treat the threads specially or specifically, and that way, if you have 8 threads, for example, and one blocks, it goes to sleep, it's waiting for a file or something of that nature, the other 7 threads can go ahead and continue executing. They could even execute in parallel if the kernel knows about that and you have enough hardware for it. So thread support requires a thread table. So similar to a process table, if I accidentally didn't say that before, a process table is just the data structure that contains all of the process control blocks that contain all the information about the processes. So the thread table that contains all the information about threads specifically could either be in user space or kernel space depending on who is keeping track of them. So for user threads, which is what you'll be doing for lab 4, you get to keep track of all of them. Thankfully, calling it a table is a bit of a stretch. It's basically just a big old array. So it's just a big array of structures that you are using to track information about threads. So the drawback is if you have user threads, well, you also need to do your own scheduling between threads because the kernel does not know about them. So you will have to do your own scheduling in lab 4. Thankfully, you're just going to do first come, first serve, and throw them to the back of the queue. So it's going to be a dead simple scheduling algorithm. If you want to extend the lab later for some reason, you could implement whatever scheduler you want on top of them. But in both of these models, it's still the same thing where a process contains multiple threads. It's just whether or not the kernel actually knows about the rest of the threads. So if we are doing user threads, we get to avoid system calls. And if we avoid system calls, well, then for pure user threads, again, with no kernel support, they're going to be really fast to create and destroy. There's no system call or anything to do. You just essentially will create a stack and some space for local variables. You don't have to do any expensive context switches or anything like that. But the drawback is because the kernel only knows about the main thread that is executing your process, well, if you create 8 user threads, and then one of them blocks because it needs to go to sleep or something like that, well, that process just blocks and no other threads will be able to execute because the kernel doesn't actually know about them. While, like I said, on the other hand, if you have kernel level threads, they're a bit slower to create because we have to do system calls, which are slower than just actual function calls. But we have the nice benefit that if one thread blocks, the kernel can go ahead, schedule another one, even if we have only a single CPU core. And the main benefit is, well, if we actually have more physical CPU cores on our machine, then it can go ahead and schedule them in parallel. Things go vroom vroom, things go really fast, if we can run things in parallel. And we all remember the difference between parallelism and concurrency. Yes, hopefully parallel, just all at the same time. Otherwise, we just have concurrency or switching back and forth really, really fast. So all of the threading libraries you use have some component that run in user mode, and then that thread library will map your user threads to kernel threads. So there are a few ways to have this system. So you could have many to one, which is the pure user threads process. So you could have as many user threads as you want, and they all map to one kernel thread that the kernel knows about and the kernel can go ahead and schedule. So the kernel just sees one process with one thread. That's all it knows about. It is not aware there are, like, if you create 8 threads, it's just not aware of them. If you do a one-to-one mapping, that means one of your user threads maps directly to a kernel thread, and the kernel handles all the scheduling, allocating a stack, everything like that, and you just use it. It just, under the hood, would have to do some system calls, which might be a bit slower. And there is many to many, so that will map a bunch. Typically, you have more user threads than kernel threads, so this will map a bunch of user threads to one kernel thread, and there'll be some division there. So for example, you could have like 1,000 user threads and 8 kernel threads, so you might do a mapping of like 125 to one kernel thread or something like that, or something that is more reasonable, because 1,000 threads is quite a lot. So many to one is like the pure user space implementation. This is U in Lab 4. So the benefits are, like I said before, it's really fast and it's portable. I don't rely on any specific kernel or anything like that. It's just a library, just code like any other code. The drawbacks are that, like I said before, if one thread blocks, everything blocks, because that whole process would block because the kernel doesn't know about your other threads. You also cannot execute anything in parallel because, again, the kernel only knows about that single thread, so you can only switch between your threads concurrently. Nothing can run in parallel because only the kernel gets to control your hardware. So if you have one-to-one, that means we just use the kernel thread implementation. So it's just a thin wrapper around the system calls in order to make it easier to use. So for example, P threads, what we saw before, they are one-to-one. So they are actually mapped directly to kernel threads, and it just essentially gives you a number that you can use. So this will allow you to exploit the full parallelism of your machine. So even if you have like 32 physical cores, the kernel can actually schedule 32 things to run in parallel if there are 32 things to run. But the drawback is it uses that slower system call interface, and we also lose some control because in this case, the kernel is scheduling between the threads. So just like before, whenever we created 2 processes and we didn't know which one was going to run next, it's the same situation for multiple kernel threads. So we don't know which thread will actually execute at any given time. So sometimes you might want absolute control above than like setting your niceness and things like that. So that could be a plus or it could be a minus because now I don't have to rely on my own scheduler. So this is the pthread implementation. So if we use threads on Linux or Mac OS or anything like that, we assume this one-to-one implementation. Many-to-many is like a hybrid approach. So the idea is that there's more user-level threads than kernel-level threads, and you cap the number of kernel-level threads to the number that we can actually run in parallel. So if I only have 8 cores on my machine, well, I can't run more than 8 things at once, so I may as well just make 8 expensive kernel threads and then just implement user threads on top of that, so then I get my parallelism. And get the most out of my CPU, I can get that parallelism with having the minimal number of system calls using to create the threads. But, however, this gives you a very complicated threading library, and typically this comes like, this is a good idea, and then someone tries to implement it, and then it's not such a good idea because it leads to a lot of strange bugs, because you're kind of at the mercy of that user thread to kernel thread mapping. So if you have, say that same thing, you have 1,000 threads and 8 kernel threads, and you map 125 to one kernel thread, well, you're still in that situation if one of those threads blocks. Since the kernel only knows about that one thread, that thread will block, and the other 124 can't execute. So you'll have the same situation where you block, and you might not have control over that mapping, or you may get unlucky. So sometimes you run your program, it goes really fast because you got lucky with that mapping. Sometimes you run your program, it goes really, really slow because you got really unlucky with the mapping. And it's typically a giant mess to try and diagnose any performance issues. And at the end of the day, most of the performance issues will come from the fact you got unlucky. So this is apparently coming back. So if you've seen Java virtual threads, hopefully you haven't, but that's like a new feature they're touting. And it's this approach. So it will seem like a good idea. People will be like, wow, it's so fast to create threads. Then they'll start using it. They'll get into lots and lots of issues, and then they'll go back to kernel threads probably. So that is my caveat for the day, but this typically comes and goes. Usually, if you want this hybrid approach, there is an easier way to do it. Oh, wait. We'll get to that later. There's an easier way to do that, which we'll talk about later. So these threads now complicate the kernel. So for instance, if we have a process that has 8 threads in it and it calls fork, what should happen? Well, one thing that could happen is it could create a new process that is an exact copy of the original. So if the original has 8 threads, then the new one would also have 8 threads. And one of those threads would have called fork, but the other 7 would have been doing whatever, so that you just get a copy of whatever they were doing when it was forked. And that would get out of hand very, very quickly because you couldn't guarantee anything about those threads. And you can imagine, well, that also makes your process bigger and will consume more resources. So if I did a fork bomb and I had like 1,000 threads, I could fork bomb myself even faster, which would be lots of fun. So that would get really out of hand really fast. So the rule is, if you have a process with multiple threads and one of those threads calls fork, the kernel will create a new process for you, and that new process will only have a single thread in it, and that thread will be a copy of whatever thread called fork originally. So the other threads will not exist. So you have 8 threads, for example, one of them calls fork. You will get a new process that is an exact copy of the original, so all the virtual memory is all the same, but this new process will have a single thread, which is a clone of whoever called fork. So it would look like it resumes back from that fork call. Yep.
What if like main calls fork?
So if main calls fork, so the main thread is just a thread like any other thread. So you get a new process. Yeah, you get a new process, and then it would have one thread that would be a clone of the main thread that called fork, if the main thread called it. Yeah.
That means if you want to call fork, have threads carried over, you have to create threads after you call fork.
Yeah, so if you want multiple threads after the fork, you have to create them after you fork again. So even if you have 8 threads and then you call fork, the new process just has 1. So you'd have to recreate them if you want them again. Yeah. Yep. Yeah, so if you have like thread 1, 2, and 3 all living in the process, and thread 2 forks, create a new process, all the memory looks the same, but this new process will only be running a single thread that looks exactly like thread 2. So it will resume from that fork call, and there'll be no other threads that exist. So that makes life fun, right? So Linux, that's what Linux does. If it hits pthread exit, well, it'll have the same rules as before. That new process would only have a single thread. So if that thread calls pthread exit, that would exit the process, and then the process would not exist anymore. And also not involved in this course, you can imagine if I have if I fork in one thread and I have 7 other threads doing stuff, I have no idea what state they're in whenever I fork. So you might have inconsistent memory or something like that. So it's not covered in this course, but if you wanted to make sure things are consistent, there is a pthread at fork function that you can run, and it's guaranteed that it will run this function to completion before it does the fork, so you can ensure your memory is in some type of consistent state. And that's just in case you ever use this. I have never had to use that in my life because forking something that has multiple threads is generally a bad idea. I'm already using threads for something. I don't really need to fork. Or if you do need to fork, it's because you're creating a new subprocess or something. So the other fun thing, well, if I have a process with 8 threads and a signal gets sent to it, what happens? So should one thread receive a signal? Should all threads receive them? Should a specific thread receive it? Should it be the main thread? Well, it can't really be the main thread because the main thread might not exist anymore, but it could. So it would also be weird if every thread got the signal, because then if you had, say, again, 8 threads, and all 8 threads would try to be doing the same thing, so they might be fighting with each other. So what Linux does to get rid of this ambiguity is it makes it more ambiguous. It will pick one and only one thread at random, and then that thread will handle the signal. So this makes concurrency really, really hard, because that signal handler is an example of concurrency. It will stop that thread from executing, switch to your signal handler, execute that, and then switch back to whatever that thread was doing. So this makes it really hard because you have no idea what thread is even going to get the signal. So you have to make sure you code your program such that any thread could receive the signal and handle it safely. And that's generally why people hate signals, and why we already looked at signals. I will not make you do signals with multiple threads because it is a giant pain. Generally, people just completely avoid it. So here is what you can do instead of doing that many-to-many or hybrid approach. You can use something called a thread pool. So the goal of many-to-many was just to avoid creation cost. What you can do instead of just depending on the library to do it is just use something that uses straight up kernel threads. And you create a thread pool, so a certain number of threads that equals the number of cores you have on your machine. And then you also create a queue of tasks. So you just create, say I have 8 cores, I would create 8 kernel threads and then a queue of tasks, and then I would never destroy any of the threads. And in the run function for every thread, it would try and get a request and then process that request and keep on reading from that queue while it has some work to do. If one becomes idle, then it doesn't have there's no tasks in the queue. If I add a new task and a thread is sleeping, I can go ahead and wake it up and have it do some work. And then when there's no work, it just goes back to sleep. So I only create my threads once, and I just have them in an infinite loop, accepting tasks, waiting for new tasks to come in. And that way it's more explicit, and it has the same benefits as that hybrid approach. So you can even do this in Python. In Python, there is a thread pool, and now you know what a thread pool is. So if you want to make things go in parallel really, really fast, and you don't want to create lots and lots of threads. So for example, if your tasks were really small and you had like thousands or billions of them or millions of them, well, just create a queue of the tasks and create a thread pool to handle it, and then you'll be able to do that in parallel. Your program will go really, really fast. So this is what you will implement in Lab 4. So you're going to implement many to one. So they're all user level threads. They're all sharing the same kernel thread. So here's a state diagram for a process. It also describes a state diagram for a thread. So you will create a new thread using this function that we will name whatCreate. Why? Because I thought it was entertaining. Stands for wacky user threads. And I don't know, it brings me joy. I'm easily entertained. I thought it was a funny name. So if you do the whatCreate, well, that should create a new thread. So that creates a new thread, and we'll throw it on this waiting or ready queue. So you create a new thread. It will not initially start executing. Remember, you are just sharing that same kernel thread. So it will go on a ready queue. So that is one of the things you will need to implement. And by implement, I mean that I will show you how to use a library queue so you don't have to implement your own linked lists. And I will show that to you in the next lecture. So you can just use an off-the-shelf one. So while it is in the ready state, well, there'll be a thread running initially. And in this lab, the context switching, they're going to be called cooperative threads. So any context switch between threads is going to be explicit. So whatever thread is currently running, it can call whatYield, and that will essentially put itself on the back of the ready queue and let the next thread in line run. So it'll just be a FIFO queue. So if a thread calls whatYield, it will go ahead and put itself in the ready queue, and the next thread will go ahead and be put in the running state and start executing. So it will do like a context switch, and again, that is what we will go over in the next lecture. You will not have to do the context switching yourself. There is a nice helper library that will do all the hard parts for you, like setting all the registers and saving all the registers. So I'm not going to make you individually save every register, because that would just be you writing like lots of lines for no educational purpose. You should just know that, hey, saves registers. So that context switch will all be done through those helper functions, and we'll go over them in the next lecture, and that will do the context switch for you. So eventually, whenever some thread is running, there will be an exit function, and that should terminate the thread. So now that thread can no longer run. If there are other threads to run, it should go ahead and execute the next thread in the ready queue or the waiting queue, and then some other process would have to essentially acknowledge this to clean it up. We're not going to have any detached threads in this. All our threads are going to be like joinable threads. So it will exit, and if it's the last thread, it should exit the process. Otherwise, some other thread that is running may be able to join it. So if a thread tries to join it, it will be a blocking call, which means that whoever called whatJoin, they are waiting on some thread to terminate, and they can no longer execute because they're waiting for that thread to terminate. So it will be put on another, you don't have to do an explicit queue, you can if you want, but it will be put in this block state, so it cannot execute because it's ready, waiting for another thread to terminate. Eventually, whenever the thread it's waiting for terminates through doing something like exiting, well, then it would be just stuck back in the ready queue because it can now execute, because whatever it was waiting for or joining on is now terminated. Well, any questions about this? So this is mostly here to help you and give you guidance, because I haven't released the Lab 4 documentation yet. And again, please provide feedback. I'm adding more stuff to the Lab 4 one because I'm getting the sense that it should have more stuff, but I don't know, you guys need to say something. There's a whole feedback channel. Please let me know. So this one, hopefully with the next lecture, should be pretty good to get started. I even ordered the test cases in a way that makes sense, and you can just implement a little bit, get some progress, feel good about ourselves, and carry on. All right, so the scheduler for that, it could be round robin, it could be whatever. So we're going to use, it's going to be kind of like round robin, except we're not going to essentially kick them out. They're going to have to requeue themselves explicitly. So you're just going to create a queue or a list. Again, you don't have to do this yourself. I will show you how to use an off-the-shelf one. And the rules are simple. It's first in, first out. So whatever is at the front of the queue is the next thread I need to run. And whenever a thread yields, it gets thrown at the back. Obviously, there is some caveats here. So if it is the only thread and it yields, well, it should just continue running because there's nothing else to run. So if you want, you can implement it going to the back, and then the back is the front, so you can execute yourself. You can do whatever you want. So you'll also have to do the context switching. You have to save the registers. Again, I will show you how to do this in the next lecture. And these are going to be cooperative threads, so they have to be nice. A simple thing you could do to make this more realistic and more like the actual kernel is making this preemptive is actually not that difficult. You can just set up a timer interrupt to come in through a signal, and then that would call the yield. So the threads don't get to control when they call yield. It would just be like every so often you could generate a timer signal, and then you call yield for them. So it would automatically switch which thread is executing without them having any say in the matter. So here is our next complication. So at this point, so what are we, lecture 17. So this is the official, you're done any midterm testable stuff. So from this point on, it will not be on the midterm. Midterm is only lectures 1 to 17. So this is going to be our next problem with threads. We will figure out how to solve this, but you do not need to know how to solve this for midterm stuff, which is also like still in a month anyways, because reading week is in a very weird time. So let us go through this problem. So what you should be able to do is, create threads and argue about the execution, and like normal execution where they're otherwise independent. This case will be a bit different. So if we execute this program, we will have a main thread that starts executing main. What it will do is create an array of pthread types up to num threads. In this case, num threads is 8. And then it is going to do a for loop. So for every thread, it will create a new thread. So this should create 8 threads, and 8 threads that want to run this run function, which I will show you in a bit. The next thing, after creating all 8 threads, then the main thread is going to join all 8 threads. So it will block and wait for all 8 threads to finish running. After that, it will print this counter variable. What is this counter variable? I'm glad you asked. So this counter variable is a global variable that you can only access in this .c file, and that is what static means. So static just means I can only access it in this C file. Other than that, it is just a global variable that I initialize to 0. Now, in my run, every thread will loop 10,000 times, and it will increment that counter by 1. So it will increment it by 1. So my question to you is, after all 8 threads are done running, what should the value of this counter be? So I have 8 threads. Each of them increments the counter 10,000 times. Yep. Around 80,000. Yeah, it should be 80,000. 80,000. All right, 80,000. So this is my program that's going to compute your marks really, really quick. So if you get 80,000, you get 100. So let's see what marks we get today. 70, that's not bad. 78. Let's run it a few times. 80,000, no bugs, no problems. Run again, 80,000. Ooh, ouch. 40,000. Almost failed on that one. So this is different every time. Anyone have any guesses as to why this is? Because this is the hardest part of the course. Yeah.
Well, maybe like multiple threads try to edit the increment at the same time, and then like it just accidentally loses one of
Yeah, so they probably didn't cover this in other courses, but let's see. Does anyone know what this actually does if it is a global variable? So where does this global variable exist? Yeah. Below the stack, so yeah, somewhere below the stack, just some virtual memory that the compiler decides that that variable's at. So because of that, it's shared between every single thread, right? So that just lives at some virtual address, and they're all modifying it. So this instruction is actually, or this line of code actually does 3 things in that line of code. So what it actually does is, and we will go over this a few times, so don't worry if it doesn't make well, it should kind of make sense, but we will also go over it again. So ++ counter. If it is a global variable, it's at some virtual address. So this actually does 3 things. In a thread, let's see. So let's say thread 1. What your computer will actually do is it will read that from memory and put it into a register. So I'll just call it register. So it would read from memory whatever the address, or read the value at the address of that global variable. So if it's at address, I don't know, 8,000, something like that, it would read the memory at address 8,000, and then whatever that value was, it would stick it in a register, which would be specific to a thread. So the next operation it would do is it would increment that register. So it would just add 1 to that register. That is a CPU instruction that you probably did in, what, is it 243 or 244? 243, okay. So 243, that's what it would do. And then the last thing it would do is it would store the register at whatever the address is of the counter, right? So it would write that value out to whatever that memory location was, right? So if initially, let's say the value of the counter is 0, well, what would this thread do? So I missed my I. So if the initial value is 0, what would this thread load into its register? What value would it get? 0, right? Counter is 0, so it would read 0. So in this case, the register would be equal to 0. So if I increment that register, what is its value now? 1, right? Just increments, just adds 1 to the register. And then if it stores the value of the register at that memory location, well, that should mean that counter is now equal to 1, which is fine. Any questions about that? So that's low level what would happen. So the problem we are encountering is, well, we have multiple threads. So say we have another thread, thread 2. So I'll get rid of these. So if thread 1 did this, it updated the value of the counter from 0 to 1, and then we context switched over to thread 2, so this is concurrency. What would thread 2 load into its register? Huh? 1, right? So one thread updated the value to 1. It's a global, so it will be available in the other thread. So if the other thread goes ahead and reads that memory location, it would read the value 1 into its register, It would increment it, so what should the value of the register be now? 2, hopefully. And then it would store it, so it would update that counter variable equal to 2. Yep, right. All right, so the bad thing that can happen is, remember, we don't control whenever context switches happen. They could happen in very bad orders. So what could happen, let's erase all of this. Instead of thread 1 running those 3 instructions and then thread 2 running those 3 instructions, we might get in a situation where thread 1 only loads the variable and then say it context switches over to thread 2 and then thread 2 starts executing. So in this case, again, if counter is initially 0, what would thread 1 read into its register? 0, right? So it would read 0 into its register, and then we context switch over to thread 2. What does thread 2 read in its register? 0 again. So it reads 0, and from this point on, it doesn't really matter what executes in any order. We're kind of screwed. So thread 2 might increment its register. Its register is now 1. Then it would store that to the address of the counter. So counter would get updated to 1. And now we context switch back over to thread 1. So it would increment its register, which again, remember, registers and the stack is private to a thread. So thread 2 executing has no effect on it. So it would increment its register, which was 0. And when it goes back to it, it's still 0. So its register value is now 1. And then it would store that value at the address of the counter and update it. So now counter equals to 1. So both threads try and increment it, but instead of them running sequentially and the value being 2, it's 1 because they both write 1 to it and we lose some of our count, which is why in that example, whenever I run it, basically it just tells me how unlucky I got because the number will always be less than 80,000 because I'm essentially missing counting some things. So sometimes I got really lucky and I executed it, in fact, 2 times in a row. Should buy a lottery ticket today. I got it right twice in a row, but other times when I run it, not so lucky. 76, 65, 80,000. My program works. So yeah, this is where it gets really hard because you have no control over that, right? You have to write it in such a way that that always works. Otherwise, you get bug reports and you have, if you thought debugging was hard before, does that look a lot harder? Because it's not the same every single time. So with this, do we have any ideas how to fix this? Can you make this print 80,000 every single time? Oh. Yeah, so there are ways to manage this. We'll get into them later, and doing that is like the hard part of the course. But without knowing anything new, can I make this print 80,000 all the time? But yeah, you're on the right track with what we'll see. Yeah.
You like create a local variable and run to count and then add to the global at the end of the function of that close service?
Yeah, so essentially, well, skipping steps, essentially you just want something like that, right? But so you might be less likely because there's only 8 threads fighting for 1. In fact, let's see. They'll probably complain at me. So 80,000, 80,000. Yeah, it kind of works. But it also has this fundamental problem, right? So it's the same situation as this, but instead of incrementing, I just add 10,000 to it. But I'm still updating, so I can have this. It's just that this only happens 8 times, So it's just really unlikely, but it could still happen. So I might get so if I get unlucky, it will be off by like a factor of 10,000. So I'll either see 80,000 or 70,000 or 60,000 or 50,000. Just depends on if one of those writes gets missed. But this makes it less likely to happen, which makes it harder for you to debug, because you will get like 1 out of a million. People will just be like, yeah, it broke. And you'll be like, oh, how do I recreate that? I have no idea. So, all right, any other ideas to how to make this always do 80,000? Yeah?
Instead of returning null, just return 10,000, and then you can make once you join all of them, then you add up all the results.
Yeah, so one idea is, well, I could join them all and get a return value from them, and then the main thread can go ahead and add them all up. Instead of that too, I could also, if I wanted to, local. So I could do something like this, and then like just create an array, one for every thread, and then have each thread just only change its specified index, and then there's no problem with that because it's just one thread updating it. And then the main thread could go ahead and add them all, sum them all up at the end. So that, hey, guess what? You just invented something called essentially MapReduce. You invented like Google's big thing. So that's like high performance computing, big data. You did the big data thing. So you don't need to take the big data course anymore. You just came up with the answer yourself. So that's how to make things run really, really fast. Just do each individually and then just add them all up at the end really, really quick. And then it pretty much runs as fast as it can. All right, any other way without changing any other code? So what if I did something silly like this? So would that be always 80,000? Should be, right? So if I go ahead and do this, hey, it's 80,000 enough times that, I mean, I'm not super confident. Well, in this case, you have to argue about it, right? With these types of programs, you always have to argue about it. So this, it should always be 80,000 because I create one thread, it modifies it, so it's the only thing running, and then I wait for it to finish. Then I create another thread, let it run, let it finish, create another thread. Does that sound like a good idea? Yeah, there's only one thing is running at any particular time. So I might as well have just written 2 for loops instead, and then it probably would have been faster than this version of it, because this version does the serial version, except creates threads and just does some extra work. So after this course, I guarantee, well, especially your employers will be like, please make this program faster. And you'll be like, I know what to do. I will make it threads. And then you will have some problems with it. And then eventually, if you want to make it safe, you essentially make the whole thing serial. And then guess what? You have made it slower and you have lost money. So that is something you always have to be wary of. Threads are not a one-size-fits-all, just boom, program go faster. You have to make sure that it is safe, and you also want, there's also a trade-off. Well, the less safe you make it, the harder it is to get right. So serial versions are easy to get right because this isn't a problem. But the real problem is trying to make it safe, which is like the hard part of the course, which we'll figure out how to do later. We'll like have a week for it. It'll be great, have a lab on it. Figure it out. We'll make things go vroom vroom much faster. All right, any other questions or anything like that? All right, cool. Let us hit the summary slide and skedaddle. So both processes and kernel threads, they enable parallelization. Each process can have multiple kernel threads or multiple user threads. Most implementations will either be one-to-one, so every thread is a kernel thread, or many-to-many, but P threads are just one-to-one. The operating system has to handle what happens with forking if I have multiple threads or signals. Now we have what is called synchronization issues, which was that problem I outlined, and you will figure out how to fix, which we'll come back to after I show you the stuff you need for Lab 4. So next lecture, Lab 4, you should probably go to that one if you want to start Lab 4, because you start Lab 4, and then we'll go back to synchronization issues, which will be the hardest part of the course, which thankfully will not be on the midterm, and then we'll ride the rest of the course to the end, and it will be lots of fun. So, just remember, pulling for you, we're on this together.